Section 15.4 Geometric Sequences. So suppose we have the following sequence 2, 6, 18, 54, etc. Then we notice that, well, if I multiply 2 by 3, I get 6. By 3, I get 18. By 3, I get 54, etc. And so if I keep multiplying each of these terms by the same amount, we say that it is a geometric sequence. And so I can characterize a geometric sequence as follows. So a geometric sequence is, well, for any natural number n, a sub n plus 1 is just equal to r times a sub n. Where, well, let me assume that r is not 0. Otherwise, you have just a whole sequence of a whole bunch of zeros. And let's assume that r is not 1. Otherwise, I just have a constant sequence where every term is just equal to the same thing. And let me assume that the first term is not 0. Otherwise, I just get a whole bunch of zeros. And so, another way to characterize the geometric sequence is as follows. So sequence is called a geometric sequence if the ratio of any two consecutive terms is always equal to the same ratio, the same ratio um, r, and let's assume that r is not 0, 1, and this is called the common ratio. Okay, so let's do some examples. Let's say on page 656, let's do problem number 2. And so I have here in exercises 1 through 5, find the first 5 terms of the geometric sequence using the given information. Okay, so a sub 2, a sub 1 is equal to 2, and r is equal to negative 1. And so the first term is 2 times negative 1, negative 2, times negative 1, 2, times negative 1, negative 2, times negative 1, 2, etc. And so that is my geometric sequence. Let me do problem number 4. And so in problem 4 it says that the first term, a1, is 3, and that the ratio a4 divided by a3 is 2, which means that, well, the common ratio will be 2. We're assuming this is geometric sequence. So the first term is 3 times 2, 6, times 2, 12, times 2, 24, times 2, 48, etc. And so, just like in the previous section, we can characterize what the general term of my geometric sequence will look like. So, general term of a geometric sequence. And so the general term of a geometric sequence is a sub n is equal to a1 r to the n minus 1. With the same sort of stipulations about a1 and r. So proof, let's use the principle of mathematical induction to prove this. So let me look at the initial case. So a sub 1 r to the 1 minus 1 is equal to a1 r to the 0, which is a1. Well, if r is not 0, then any non-zero number to the power 0 is just 1. And so a1 times 1 is just a1. So therefore, I've shown that an is equal to a1 r to the n minus 1 when n is equal to 1. So I've shown that the initial case works. So let's look at the induction case. So let me suppose that a sub k is equal to a1 r to the k minus 1. Then ak plus 1 is equal to r a sub k, just by the characterization of the definition of a geometric sequence. And so is this equal to, well, a sub k by the supposition is a1 r to the k minus 1. So by the properties of exponents, this is equal to a1 r to the, well, k minus 1 plus 1, which is by the commutative property of addition. It's k plus 1 minus 1. And so I've shown that, maybe I'll say it this way. So therefore I've shown that the induction case works. So I've shown that if ak equals a1 r to the k minus 1, then ak plus 1 equals a1 r to the k plus 1 minus 1. So therefore, so I've shown that the induction case works. So therefore, since both the initial and induction case works, then by the principle of mathematical induction, so therefore by the principle of mathematical induction, the formula works for all natural numbers. For all natural numbers. Yeah. So I'm done. Okay. So let's do problem number 6. In exercises 6 through 8, Find the first 5 terms of the geometric sequence. Okay, so we're given that a sub 3 is equal to 24. A sub 7 is 384. And I want that all terms are positive. Okay. And so, well, I know that we've just shown that the general term for a geometric sequence has the following form. A sub n is equal to a1 r to the n minus 1. And so, when n is 3, the general term for the geometric sequence says that a sub 3 equals a1 r to the 3 minus 1. And so, I know that a sub 3 is 24, and 3 minus 1 is 2. If I let n equal 7, then a sub 7 is equal to a1 r to the 7 minus 1. And while a sub 7 is 384, that's what we've assumed here. And 7 minus 1 is 6. And so I have that here. I have 384 is equal to a1 r to the 6. And I have that 24 is equal to a1 r squared. Therefore, their ratios are equal. And so 24 divided by 384 divided by 24 is 16. Again, assuming a sub 1 is not 0, which is our general assumption in this section. I can cancel these. And again, I can divide both of these by r to the r squared. So I get r to the 4th. So therefore, I get 16 equals r to the 4th. So by the square root property, actually, let me do it this way. Let me not use the square root property. Let me subtract 16 from both sides of my equation. So I get r to the 4th minus 16 is 0. I can factor r squared minus 4, r squared plus 4 is 0. I can factor r minus 2, r plus 2, r minus 2i, r plus 2i. Okay, so I can factor each of these and set each factor to 0. R minus 2 is 0. R plus 2 is 0. R minus 2i is 0. R plus 2i is 0. Add 2 to both sides of your equation. Subtract 2 from both sides of your equation. Add 2i to both sides of your equation. Subtract 2i from both sides of your equation. And so r is equal to 2. R is equal to negative 2. R is equal to 2i. R is equal to negative 2i. Well, so now I look and I want all terms to be greater than 0. So they can't be any of the complex solutions. It can't be negative either. It can only be positive. So in this case, after that's all said and done, I really can only choose the one that is greater than 0. So I'll choose positive 2. And so I have here that 24 equals a1 r squared. So 24 is equal to a1 r, which is 2 squared. And so 24 is equal to 4a1. divide both sides of my equation by 4. And so I have that A1 is equal to 6. So therefore, A1 is 6, R is 2. And so the first term is 6, next one 12, 24, 48, 96, etc. Okay, and so that's the first 5 terms of the sequence. Let me do problem number 8. So again, we want to write out the first 5 terms. So a sub 1, problem number 8, a sub 4 equals negative 1, a sub 10 equals negative 1, and it says that the terms alternate between being positive and being negative. This is actually called an alternating sequence. Oh, don't write those too close. And alternating, alternating, alternating sequence. Okay. Let me. So, uh, so therefore, well, uh, I know that the general term for a geometric sequence is characterized by, well, a sub n is equal to a1 r to the n minus 1. And so I know that when n is equal to 4, this gives a sub 4 equals a1 r to the 4 minus 1. Well, a sub 4 by the above assumption is equal to negative 1. And 4 minus 1 is 3. Let's look at a sub 10. So let n equals 10. So if n equals 10, then plugging in 10 for n, 10 for n here, I have a sub 10 is equal to a1 r to the 10 minus 1. And by the above assumption, a sub 10 is negative 1. And 10 minus 1 is 9. Therefore, I have that negative 1 equals a1 r to the 9. And from above, a1 is equal to, negative 1 is equal to a1r cubed. Therefore, their ratio are equal since both the numerator and denominator are the same. So negative 1 divided by negative 1 is just 1. Again, assuming a1 is not 0, I have that I can cancel the a1s. And again, r to the 9th divided by r cubed is r to the 6th. Again, I'm assuming that r is not equal to 0. And so I have, finally, that r to the 6th is 1. Okay, and so let's try to solve that. So let me subtract 1 from both sides, because there'll actually be 6 solutions, I guess. So r to the 6 minus 1 is 0. Factor r cubed minus 1, r cubed plus 1. We remember from way back in, I think, chapter 3 or 4 when we, chapter 4, I think, when we did these, that it's better to, it's much easier if I factor it in this manner, rather than doing the treating this as a difference of cubes at the beginning, treated it as difference of squares at the beginning. So now I can factor this. R minus 1, r squared plus r plus 1, r plus 1, r minus r squared plus 1 is 0. Therefore, r minus 1 is 0. Seti's factor is 0. Use the zero factor property. R squared plus r plus 1 is 0. R plus 1 is 0. Or finally, r squared minus r plus 1 is 0. And so, adding 1 to both sides, subtracting 1 from both sides, I get r equals 1. R equals negative 1. To solve these, well, I'm going to have to use the quadratic formula. So r equal negative b plus or minus the square root of b squared minus 4ac all over 2a. And so I have r is equal to, so let's try to solve this equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. So r is equal to negative 1 plus or minus the square root of negative 1 squared is 1. 4 times 1 times 1 is 4 over 2. So r is equal to negative 1 plus or minus the square root of negative 3 over 2. And so r, good afternoon. So r is equal to negative 1 plus or minus I rad 3 over 2. Or, well, let's do the other one. So r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So r is equal to 1 plus or minus the square root of a negative 1 squared is 1. 4 times 1 times 1 is 4 over 2. So r is equal to 1 plus or minus the square root of negative 3 over 2. And so I get I get r is equal to 1 plus or minus I rad 3 over 2. Okay, so I want that here it is. I want an alternating sequence. So if I let r equal 1, well, I'll get all the signs are the same, so that will alternate. And if I let r to equal either of these uh, complex ones, well, I won't get alternating sign. I'll get a whole bunch of complex numbers, so I don't want those. So the only one that works really is r equal negative 1. So after all that, well, there's only one that really works, r equaling negative 1. And so let me do that. So I have that, well, negative 1 equals a1 r cubed. So let me use that. So negative 1 equals a1 r cubed. Okay, so negative 1 equals a1, well, negative 1 cubed is just negative 1. Divide both sides of the equation by negative 1. And so you get that a1 is equal to 1. So therefore, I get first term is 1 times negative 1 times negative 1 times negative 1 times negative 1, etc. And so it keeps alternating between plus and minus 1. And that's your answer. Okay. Let me do problem number 10. No, let's do problem 12. Negative 3, 6, negative 12, 24, etc. In exercises 9 through 14, find the general term for the given geometric sequence. Well, I know that the general term for a geometric sequence is just an equaling a1r to the n minus 1. And so an is equal to, well, the very first term is negative 3. The common ratio, well, to go from negative 3 to 6 to negative 12 to 24, I have to multiply by negative 2. So notice each time I multiply by negative 2 to get the next term. And so that is the characterization for the general term of this geometric sequence. Let me do problem number, well, let's say 14. Negative 1/4, negative 1/12, negative 1 over 36, negative 1 over 108, etc. And so, again, I want to determine the general term for this geometric sequence. So, I have that a sub n is equal to a1r to the n minus 1. Well, the very first term is negative 1/4. Next, to go from negative 1/4 to negative 1/12 to negative 1 over 36 to negative 1 over 108, etc. Notice that each time I'm going to be multiplying. Notice the signs don't change. So I'm multiplying by a positive. And well, to go from 4 to 12, that's 3. Times 3 is 36. Times 3 is 108. Therefore, I keep multiplying by 1 over 3. And that is the general term for this particular geometric sequence. Let me do problem number 16. Find the geometric mean of negative 3 and negative 27. And so the geometric mean for the for two numbers will just be the square roots of their product. In general, the geometric mean for n numbers will just be the nth root of their product of those n terms. And so let's see, this is equal to 81, and the square root of 81 is 9. So the geometric mean of these two numbers is 9. Note that what we've really done is we've just inserted a term to make this a geometric sequence. And so notice that what we've really done is we've inserted something so that, well, negative 3 times negative 3 is 9, times negative 3 is negative 27, etc. So I've really just inserted some term to make this a geometric sequence, just like in the previous section, we inserted a term to make a arithmetic sequence, and we call those terms arithmetic means. And so let's do this. So problem 16, problem 18. So let me do problem 18, which says to insert two geometric means between 5 and 40. So we have the first term, second, third, fourth term, and then the fifth term. And so I want to insert these three numbers so that this now is a geometric sequence. Okay, well, I know that if this is a geometric sequence, then the general term for geometric sequence is just a sub n is equal to a1 r to the n minus 1. And so I have here that, well, the first term is 5, and the last term, which is the fifth term, is 40. So using the following general term, I have that the fifth term is equal to the first term times r to the 5 minus 1. So a sub 5 I know is 40. A sub 1 I know is 5. 5 minus 1 is 4. Divide both sides of my equation by 5. So I have insert two geometric means. That makes my life much easier. Okay, and so they just want two geometric means, not three. So two geometric means. And so 4 minus 1 is 3. Divide both sides of my equation by 5. So 8 equals r cubed. Subtract 8 from both sides. So I get that r cubed minus 8 is 0. I can factor this. R minus 2, r squared plus 2r plus 4 is 0. I can set each factor to 0 and solve for r. And so adding 2 to both sides, I get r is equal to 2. Using the quadratic formula, I get the following. And so r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So r is equal to a negative 2 plus or minus. 2 squared is 4. 4 times 4 is 16. 2 times 1 is 2. 4 minus 16 is a negative 12. I can write 12 as negative 4 times 3. And so you get negative 2 plus or minus 2I rad 3 over 2. I can factor out a 2. And so I get 2 times negative 1 plus or minus I rad 3 over 2. So the 2's cancel. And so you get 1 plus or minus, negative 1 plus or minus I rad 3. But you don't want complex common ratios because we only want to look at real solutions. And so R is just equal to 2. Okay. We also have that, we know the first one. So it looks like 5, 10, 20, 40. So the two geometric means are 10 and 20. Okay, so that was problem number 18. Let me do problem number 20. 4, negative 8, 16, negative 32, and then a whole bunch of terms, negative 5, 12. In exercises 20 through 24, find the number of terms in the given geometric sequence. And so let's do that. I know that a sub n is equal to a1 r to the n minus 1. And so let's just look at the nth term. So the last term. So let's just plug in n into this and figure out what happens. And so the last term is, well, negative 512 is equal to a1. Well, I know what a1 is, 4, times r. Well, that's the common ratio. To go from 4 to negative 8 to 16 to negative 32, I have to keep multiplying by negative 2. And so, I don't know what n is. Let me solve this equation. So let me divide both sides of my equation by 4. And so I get negative, so multiply by 4. So I get negative 128 is equal to negative 2 to the n minus 1. I know that 2 to the 7 is equal to 128. So negative 2 to the 7 is equal to negative 2 to the n minus 1. And so since the exponential function is 1 to 1, and since the bases are the same, then the exponents must be the same. And so 7 is equal to n minus 1. So adding 1 to both sides, I get that n is equal to 8. So there are 8 terms in my sequence. Let me do problem number, let's say 22. 2, 6, 18, 54, 13,122. Let's find how many terms in this sequence. And so I'm going to do the exact same thing. The general term for a geometric sequence is characterized by the following formula. A sub n is equal to a1 r to the n minus 1. And let's look at the last term, the nth term. And so if I do that, then I'll be able to figure out what n is because I know everything else. So let's look at the nth term. The nth term. And so I have that 13,122 122, a sub n, is equal to a sub 1, 2, times r, well, to go from 2 to 6 to 18 to 54, I keep multiplying by 3. So the common ratio is 3. Divide both sides of my equation by 2. Oops. And so 65, 61 is equal to 3 to the n minus 1. If you don't know, actually this is probably best. Uh, suppose I don't know that this is 3 to some power. So let me try to solve this exponential equation. I could have done that here also, but let me solve this exponential equation by taking ln of both sides of my equation and solving for n. And so by the properties of logarithms, I know that I can bring the exponent out in front of the logarithm. Let me multiply ln 3 inside the parentheses. By the distributive property, I have ln 6561 equals n ln 3 minus ln 3. Let me add ln 3 to both sides of my equation. And so I have that ln 6561 plus ln 3 equals n ln 3. So let me divide both sides of my equation by ln 3. And so I have that n, oops, the n is equal to ln 6561 plus ln 3 over ln 3. You can plug that into your calculator and you get 8. Or just know the fact that 3 to the 8, 9 is equal to 9. And so if you plug that into your calculator, uh, you can simplify that and you just get the number 9. Okay. So let me do problem number 24. 5, 15, 45, 135, 98, 415. Oops. Multiply by 3. Yes. So in this case, you're going to be the common ratio will be 3. And so so again, I want to figure out how many terms in this sequence. So a sub n is equal to a1 r to the n minus 1. So again, looking at the last term, the nth term, I have that a sub n, which is 98, 415, is equal to the first term, 5, times the common ratio, 3, to n minus 1. So notice to go from 5 to 15 to 45 to 135, I have to keep multiplying by 3. Divide both sides of your equation by 5. So then you can solve this exponential equation. So 98, 415 divided by 5 is 19,683. And so I can try to solve this again using the same thing that I did above. So this is take ln of both sides of my equation. And so ln 19,683 equals n minus 1 ln 3. Multiply the ln 3 inside the parentheses using the distributive property. So I have that ln 19,683 equals n ln 3 plus ln 3. Subtract ln 3 from both sides of my equation. And so I get ln 19,683 minus ln 3 equals n ln 3. And so divide both sides of my equation by ln 3. So n is equal to ln 19,683 minus ln 3 over ln 3. You can plug that into your calculator. If you plug that into your calculator, you get 10. I guess there's just one more term in that sequence then. Okay. Oh, yeah. And so there are 10 terms in this sequence. Let me do problem number 26. 1, 2, 4, 8, etc. In exercises 25 through 28, draw the graph of the given sequence. Okay, so a sub 1 is equal to 1, a sub 2, 2, a sub 3, 4, a sub 4, 8, etc. So this says that a evaluated at 1 is 1, a evaluated at 2 is 2, a evaluated at 3 is 4, a evaluated at 4 is 8, etc. And so I can draw this. Or maybe I'll call it a sub n. Okay, so 1, 2, 3, 5, 6, 7, 8. 1, 1, 2, 4, 5, 6, 7, 8. Okay, so let's see. A sub 1 is 1. A sub 2, 2. A sub 3, 4. A sub 4, 6, 8, etc. And so, if I look at this, notice that it looks like an exponential. So this just looks like an exponential function. And so this is just some sort of exponential function here. Okay? So if I kept going more and more, the graph of it would just look like what we saw in the previous chapter, the graphs of an exponential function. Yes. Yes, the line would be curved. So basically, it looks like graph of y equal 2 to the x. So if I look at this, it just looks like some values, well actually 2 to the x minus plus 1. It looks like the graph of that. No, if it looks like that. So it looks like, and so if you just plug in, oops, this graph. So that's just these few, 1, 2. So I just plugged in like these 4 points along that curve. Okay, so it looks like the graph of that function, uh, except we just put in these 4 numbers into that graph. Okay, so yes, it would be curved. It'd be growing exponentially. Okay, so for a arithmetic sequence, the graph of it basically looked like a line. For a geometric sequence, the graph of it looked like an exponential. Okay, so that's how they were characterized. So that really finishes off section 15.4. Let me go on to section 15.5. Which is, arithmetic series. Okay, so let me close this. Okay, so let me just 1 second. Let's see if I can close this. There it is.